Companies hire people to hang advertisement flyers on doors in neighborhoods. The company took a random sample of 12 people in hopes of estimating the flyers they can hang per hour. The scatter plot displays the results. Excel calculated the regression line to be basically y equals 50x, meaning that on average people hang 50 flyers per hour. Two people in a sample both worked 6 hours. One delivered 330 flyers, which is 55 flyers per hour. The other delivered 270, which is 45 flyers per hour. The regression line cuts through the data in a way that tends to average all the results. In this case, the regression line gives a rate of 50 midway between the 55 and 45 flyers per hour. Note as well that the y-intercept is basically 0, 0. This makes sense because 0 hours worked, no flyers hung. Warning, I made up this data so that I could provide a foundational understanding. In reality, rarely do you get a y-intercept of 0 with the regression line, even though you know it's supposed to be 0. And rarely do we have points that are exactly 5 flyers per hour above and below the regression line. So let's add some sophistication to this and make a huge point regarding real-life phenomena. Now pay close attention. This is one of the most important concepts in all of statistics. Random chance fluctuation tends to follow a normal distribution with its empirical rule of 68, 95, 99.7%. Let's suppose that 50 flyers hung per hour is the true exact slope, rate of change, rate of flyers being hung. So what would we expect to have happen if we randomly selected many people who all worked 6 hours? Well, by golly, I'm glad you asked. Suppose the standard deviation is 20 flyers. We would expect 68% of all flyers hung in 6 hours to be within one standard deviation of the 300 flyers predicted, so between 280 and 320. We would then tend to see another 27% from 1 to 2 standard deviations away for a total of 95% of the results between 260 and 340, and then less than 5% of the results would be outside of that. Now the same random normal scatter should occur for those who spent 4.5 hours delivering, and the same random chance fluctuation should occur for people delivering 3 hours. What happens then whenever we take a random sample is that we cannot control this random chance fluctuation. The next sample we get may have an overrepresentation of higher results still with reasonable scatter. In this case, our regression line may look like this and have the equation y is equal to 54.2x minus 5. The 54.2 flyers per hour is no big deal, but how do we explain that y-intercept is 0, negative 5? Worked 0 hours, delivered negative 5 flyers? Makes no sense. But this usually happens when we calculate a regression line because each new sample is introducing its own random chance fluctuation. So do not worry about a y-intercept that is not even possible. It's usually the slope we're trying to determine, as in the case of the flyers. In a second example, researchers have developed a pain reliever with very low risk of side effects. They want to see how it works on patients suffering from chronic back pain in the hope of replacing dangerous opioids as a treatment. Patients were asked to rate their pain on a scale from 1 to 100 30 minutes after taking a certain dose of this new pain reliever. The regression line in this case has a y-intercept at 0 and 74.4, implying that the average level of pain among those individuals prior to taking the pain reliever was about 74 points. The slope is negative 0.6, meaning that for each additional milligram of pain reliever given, the pain level tends to drop by 0.6 points. But remember, this is data from one experiment. Here's data from a second experiment. Each experiment has its own unique random chance fluctuation, which yields two different regression equations. The new equation has a shallower slope, negative 0.496, or about negative 0.5. This implies that the pain is dropping only by 0.5 points for every additional milligram of pain reliever. So, which line is closer to the true regression line for the entire population? Answer, we don't know. We do not know the actual pain relief per milligram of pain reliever. Later, when we get into inferential statistics, we will construct confidence intervals that are highly likely to contain the true rate of relief.